today I'll give an overview of some of the progress that's been made in Bayesian inference and Hebbian collisions. I made some editorial choice in the sense that I won't necessarily focus on certain specific results, but I try to approach more the broader picture of Bayesian inference, what I think we're doing well, what are opportunities we can still explore, and maybe some misunderstanding as well. So please, again, don't hesitate to ask if you have any questions as I go. So I think often, if we mention Bayesian inference and Hebbian collision, I think perhaps one of the more famous result, or perhaps what comes to mind, is this result on the right, or result similar to what we have on the right. Let me make sure that you can see maybe a laser. Right, so you can see my laser, right?
Yes.
My pointer, okay. So often we'll associate Bayesian inference with large-scale model-to-data comparison, where we quantify systematically the uncertainty, and often where we use emulation to achieve that goal. So I don't know how familiar everybody here is with Bayesian inference, emulation, and so on. If you're not familiar with this, I'll be discussing it more later. But of course, even if that's what often comes to mind, there's no reason to limit Bayesian inference to any of these concepts or any of these properties. So on the right here, I'm showing an analysis that has been done recently by former and current BNL researchers, and the number of data points is actually not very large. There's maybe 15 data points that they're fitting, and it's still valuable. They had a number of parameters, and it was still valuable to use Bayesian inference even with that somewhat limited number of data points. So it's certainly not the case that you should only consider using Bayesian inference when you have hundreds or tens of observables. It will be useful. It can be useful for any type of analysis. I think often we of course associate Bayesian inference with systematic uncertainty quantification. That's also something I want to discuss more today, because I think naturally Bayesian inference will provide systematic and probably precise systematic uncertainties on your parameter. But precision is not what we're after necessarily. We're after accurate, or optimally precise and accurate estimates. So I think there's work that needs to be done by the community to better understand this, or at least better communicate this when we perform Bayesian inference. And often Bayesian inference will be associated with emulation. Emulation is the idea that perhaps your model is very expensive. So if you want to know what the prediction of your model is for a set of parameters, it might take a couple hours or a couple of days to perform the calculation. But then you want to know it for multiple parameters. Maybe you're trying different viscosities, different initial conditions. You have multiple parameters. And at some point, it becomes impractical to run your model over and over again, especially if you know something about your model. For example, if you know your model is relatively smooth, you don't necessarily want to run it over and over again. You can use emulation to try to interpolate between samples of your model. Now, emulation, of course, has a life of its own. You don't necessarily need to do Bayesian inference if you use emulation. There's, I think, there's interest, and there's a lot of interesting physics we can do without doing any Bayesian inference and looking at emulators. So I'll mention this too later. Now, most applications that we've had up to now of Bayesian inference in Hebbian collision, many of them have been for the soft sector. So soft sector I know there's been presentation earlier this week about transport coefficients and momentum envelopes and so on. So presumably most of you have an idea of what I mean by soft and hard sector. So in the soft sector, we're mainly interested in the transport coefficient of the quark gluon plasma, maybe initial conditions of the system, which is really the theme of this workshop, and perhaps some other properties. And most of the analysis up to now have been focused on these properties. And also in the hard sector, where there's interest in, for example, how much energy your partons are losing to the quark gluon plasma. Now, what's in common with these different problems is that we're trying to constrain quantities that are not simple numbers. We're trying to constrain quantities, for example, the shear viscosity over entropy density. It's a function. It's difficult to constrain a function without using a very systematic approach. Same for Q hat, this quantification of the energy loss, because you have a temperature dependence, a momentum dependence. It's something that's difficult to do it's difficult to extract and systematically quantify the uncertainty without having a systematic approach to do it. And that's what Bayesian inference offers. I'd say initial conditions are probably even more challenging, in part because let's take the example of shear viscosity. We know that shear viscosity is a function of temperature. Now, it's difficult to constrain a function of temperature. You need to allow for all kind of different temperature dependence. But initial condition, there's even more flexibility in the initial conditions, depending on what you mean exactly by initial condition. Not necessarily the nucleon distribution inside a nucleus, but even how energy is deposited. So Bayesian inference is certainly a useful tool for this. And let me, in the next couple of slides, give a brief overview of what Bayesian inference is. And I'll discuss some of these results and what we can learn and where to go from where we stand as a community. So Bayesian inference comes from Bayes' theorem, which is this. So I repurposed this from this book up here. There's a relation between, so it's conditional probability, and it's the relation between your prior and your likelihood, which are the input that you're providing in this problem, is a relation, and this is equal to the evidence in the posterior. So your prior is the probability that a certain parameter has a value before you do, well, given some external information that you have. The likelihood is a probability that the data is consistent with the parameter. And the posterior is often what we're after. It's the probability the parameters are consistent with the data. And the evidence you can think of as the normalization of the prior. Now, Bayes' theorem itself, this statement, that's the basis of the that's the theoretical basis of all of this. But most of the physics and most of the modeling decision come when you pick a function for your likelihood, and you make certain choices for your priors. So the most important choice, I would argue, is the likelihood. So often people will use a Gaussian likelihood. So Gaussian likelihood looks like this exponential, and here actually I didn't put the normalization, so you have a well-defined normalization for this. Your likelihood is effectively your data minus your model prediction, and you have a matrix product that, well, you have a vector product with a matrix, and this matrix can encode both experimental theoretical uncertainties, but also any correlation that you have between your observables and between your uncertainties. And at the moment, I think we're good at including the experimental uncertainty systematically, including statistical uncertainty for our calculation, emulator uncertainty. the covariance is something that that has been explored by certain groups, but we haven't heavily explored. So actually, I don't know, maybe others in the room know better than I do, if other fields are significantly farther ahead than us in terms of including those covariants. Now, the priors are, as I said, any external constraints that you have. It can be positivity constraints. If you know that shear viscosity has to be positive, then you want to make sure that your prior forces the shear viscosity be positive. There can be external constraints from other measurements that you don't necessarily want to include in this analysis because maybe they were obtained from different sets of models. And there could be constraint also from theory. Maybe we don't have a perfect constraint on certain parameter, but maybe theory gives us an idea of the range of values.
So maybe just a general question. You do this in the model, in a given model framework.
Yes.
How do you actually handle the biases in the more intrinsic in the model? If there's a difference between the, you mentioned the precision versus accuracy, right?
Yes.
The issue. So how do you, if there's bias, there's a systematic biases, which means in the end you find some parameter which have a best description, but then those parameters are biased. And how do you quantify that in this approach?
Right. Let me come back to this question in a call slide. Actually, it's
okay.
If you ask me, it's the most important question that we need to address, and I don't think it's a controversial statement because obviously, if we had perfect models, our life would be much easier. But yeah, so I'll get back to this in a couple of slides. But yeah, it's a very important. And I use the term theoretical uncertainty to partly include what you refer to as bias. I think people use, I don't think it's a standard terminology. I think people use a range of different terms for this. Let me get back to this soon. Let me just highlight that this quantity here that we compute, the likelihood that we pick, is effectively is exponential of minus chi²/2. So in terms of novelty, I think we've all been calculating chi-squares for a long time. So novelty is not necessarily in the fact that we can define this quantity. It's the fact that it's the interpretation that we're doing of this quantity. That instead of looking often with chi-square, we tend to look at the single best value, and that's what we would call the maximum. That's generally what we would call the maximum posterior value in Bayesian inference, up to differences in the prior. But really, you have a much richer set of information if you define your posterior like this, and you look at your posterior and you look at the information your posterior provides. So let me give an example. So the simplest possible example of Bayesian inference using this Gaussian likelihood is you have model parameter, you have data with some uncertainty, and you have a model. If you compute your chi-square, you get something like this, because your model is very simple, it's analytic. And if you plot your posterior, you'll get a Gaussian, of course, because this is in 1D and you have a linear model. Now, a couple of things you can already notice from this very simple example is that first, how large your uncertainty is of course it's a factor of how much uncertainty you had on data, but of course it's not controversial, but it's heavily dependent on how much your model depends on the parameter. So if your model is weakly dependent on the parameter, you get a very broad posterior, and if your model is very sensitive, so if this slope is large or small, you can get wildly different constraint with the same accuracy on the data. So that's why it's, if we come back to heavy physics, even if you have percent level uncertainty on all your different measurement, it can mean wildly different level of constraints on your parameter, depending on how much your observable depend on the parameter. Now, in practice, the models that we have are not.
Can I have a question? Hi.
Yes, of course.
In this example, what is the prior here?
So here I think I removed it from the slide to make some room. So here I'm using a flat prior, which would be 1 between 0 and 3, and then the prior is 0 outside of this range.
So that's pretty kind of external constraint in this model, simplest model.
Yeah, exactly. I should say I won't be talking that much about prior because I think there's been only limited work on priors in heavy physics up to this point. I think we often use flat priors, which is obviously a challenge because there's no reason that flat priors would be preferred over any other type of priors. So priors will remain up to a point an open question, maybe something we can discuss more if there's interest. Yes.
Okay, thanks.
All right, so the reason that Bayesian inference is more complicated than this in heavy collision is, well, the first reason is the model is nonlinear. It's not known analytically, it's known numerically. It's relatively expensive to compute, and it's also stochastic. So all of these means that doing Bayesian inference is somewhat more complicated because your model here, just getting the value, what your model predict for a certain observable given a parameter, just getting this value is actually relatively non-trivial. Often to handle this, we use what I call emulators or surrogates. So we sample the parameter space. You divide your parameter space, for example, with a lat on a hypercube or some other algorithm. You divide it up. You compute your observable at different points, and then you use an emulator like a Gaussian process emulator that's used here to interpolate between the points. Gaussian process emulator, they have the benefit. It's not the only emulator you can use. I think people have explored, for example, Bayesian neural networks and other techniques. The benefit of Gaussian process, I think it's a mix of their, they need somewhat less data neural network because you have strong assumptions, and they're good because you can quantify, the emulator quantifies its own uncertainty.
JF,
So, yes.
Comment here.
Yeah.
So this picture illustrates very nicely what kind of theoretical uncertainties you can include in your single likelihood parameterization that you have up here. Namely, if the model is a stochastic model that produces results with a certain uncertainty, as indicated by your vertical red error bars, then you can include that in the inverse covariance up there. But
yeah.
But you cannot include the theoretical uncertainties that have to do with differently parameterized models, for example.
Yeah, exactly. Yes. Yeah. Thank you for this, Uli. So yes, so statistical uncertainty is straightforward to include in the Gaussian process. Any other sort of uncertainty, for example, choice between different models and so on, that's coming either through. You can think of parameters as a way to quantify your model uncertainty. So perhaps you don't know exactly what your initial conditions are, so you have parameters for it. So parameters in part are a way to quantify your theoretical uncertainty. And if you have literally different models, then you need other techniques that we can discuss later.
So this is the posterior, right? In this particular.
No, so this is actually the, so this axis here on the left is the output of your model. So think of this as what your model predicts for your number of pions, or your mean PT, or your V2. And think of the x-axis as what your parameters are. So it could be your shear viscosity, or some parameters for the shear viscosity, could be the total energy that you deposit in your system, and so on. So that's something that, if you're not used to this, it might sound counterintuitive, which is that so of course the model itself is not deterministic, it's stochastic. So every time you run, you compute your V2 or you compute your mean PT, you'll get a certain stat uncertainty.
But I just you have a curve there. That curve is your model, right?
So the red points are the actual output of
Right.
the model, and the blue is what we call a Gaussian process. So it's the emulator. So it's something that's trained. So think of it as a probability distribution that's trained on the red points. So it tries to get the average going through the points as much as it can. It tries to get the error bar covering as much the error bars as it can. So this would be this would be 95%. So it would be a 2 sigma uncertainty.
But this is what's the probability distribution given observation? Like the data point is the observations, right? So it's I don't
No,
which part of this formula?
observations are modeled. There are no real data here. It's modeled
observations. But so just the data difference between data and model.
No, that's not. It's not plotting the posterior. It's plotting when you calculate the observable with the posterior and average over the range of parameters allowed by the posterior with the posterior probability distribution. So this is directly calculating an observable, and in our case, there would be many observables that you would get from the same posterior that you could calculate from the same posterior.
Actually.
Yeah, we can spend a little more time on this. I'm sorry I didn't explain this well. So think of this as, if I give you a red point and I tell you to interpolate between the red points. Presumably what you don't want to do is just, for example, just train a high order polynomial on the center of the red points, right? It's going to make no sense. You're going to have huge fluctuations between the points. It wouldn't make any sense. You could use a linear interpolation of something. But ideally, you'd like to use something more, maybe more sophisticated, that can take into account the fact that, sure, you want some smoothness as you're interpolating, but you also assume that you can have some stochastic uncertainty, which means that you don't necessarily need to go through every single point. So it's really you can think of it as an interpolator. Does that make sense?
This is a part of the input that you use to calculate the posterior.
Yeah, so this will take the place of your model effectively. So it's literally, you're going to replace this model here by your blue curve.
Okay, I see.
Yes. Yes. And the reason we do this is because the model is simply too slow to try to, every time you need the value, just to try to ask the model for the value. So instead, you pre-run, then you train this blue curve, you prepare this interpolator, this blue curve, and then you discard the model, you set the model aside, and you just use the blue curve instead of your model. Any more questions about this?
So in case in this particular example, you know for sure that it's x sin x, the function is x sin x. But in real world, if you have some observable as a function of parameter and you don't know, how do you emulate it? Like how do you, like what do you?
Right. So in the real world, what you do, you think of your model as taking on one side, your model is taking, let's see, maybe I can write on this. So you have parameters that go in your model, and you have some observables. So it's the output of your model. So input, output. Now you can certainly, you can decide on a selection of input. So you can sample your input. For example, you can pick a couple of different points here. And then you take those parameters, you put that in your model, and you'll get outputs. You'll get outputs for each one. But it's true, you don't know what's the underlying parameter. You don't know what's the underlying function. You just have those samples. So what you want to do is you want something that is a flexible way to interpolate between those points. Now, the curveball that you have is that those points have an uncertainty because your model is stochastic. So each point is an uncertainty. So of course, if you have infinite amount of CPU time, you can just drive that uncertainty to negligible value if you want. But often you have to, there's some trade-off that you need to be careful about. So if you have only the green points, for example, what you'll want to do, you'll want some function that can interpolate between the points, even if you don't know what the underlying function is. So you want something that, maybe so if you literally have no idea what your function is, if you have no assumption about what your function can be, for example, no smoothness assumption, you're a little stuck because nothing prevents you from putting resonance anywhere in your model, right? Now, in general, we assume our model is smooth. Now, the degree of smoothness is a parameter of the interpolator. So if you assume it's pretty smooth, then maybe you want to say, well, okay, in between the points, maybe I don't know exactly what the value is, but it shouldn't be outside this range, for example. So your uncertainty is gonna swell. Your uncertainty of your emulator is gonna swell. So what I'm drawing is somewhat the equivalent of a blue line, but with fewer points. And so you would have something that's a probabilistic emulator that will say, if I ask the emulator at value of x equal to 6, what is the output of the model? Well, it's going to pick a value that's, it's going to sample from a distribution that's kind of peaked around some mean, but has a certain width. Does that make sense? Yeah.
Do you mean the emulator that you use is not deterministic, or you just mean it's an uncertainty associated with it?
The output of the emulator is probably
The emulators, I mean, I think the thing in practice, I think because the seeds are fixed and everything, we always get the same. Like if you sample it. But yeah, it's probabilistic. So the emulator is probabilistic. So if you
so when you're calculating this likelihood, and you have some, and you're trying to find what its value is at some point in parameter space, you ask the emulator what your model predicts, and the answer it gives you is random. Is that right?
it's not random, it's stochastic. Gives you
Is that the same thing?
no.
yeah, it should give you it should give you a distribution around the mean, right?
Value is usually all over the place.
Yeah.
Formula. How does this formula handle distributions? I'm not quite sure I understand in practice how this is working.
How does it handle distributions?
Yeah, you calculate the likelihood, and then you want to know what's the likelihood at some point in parameter space. What happens again? You don't just ask the emulator what the value of the model is, and then you plug it in here, you get a distribution. And what do you do with the distribution in this formula?
Okay, maybe we should step back. Let's assume that the model outputs are actually deterministic, so they are points, not points with uncertainties. Then you can make sure that your emulator reproduces exactly these points, but then when you use the emulator to interpolate between points, there is an extrapolation uncertainty associated with that. So that means the value that you predict, that the emulator predicts between training points, is given by a distribution with a mean and the variance. Those are these bubble graphs that he had.
Sure.
Now, because here the model output is not deterministic but stochastic in itself, you never have zero uncertainty in the emulator. So it's always, the emulator always gives you a distribution of likely values for the observer with a mean and a variance.
Yeah, and then what do you do with that distribution? I'm not quite sure I understand how you evaluate the likelihood of using the distribution in this formula.
Well, then
Instead of a-
once you have that distribution, you know what the range, the 90% or 60% confidence range of your prediction is.
Yeah, but let me think for a second. So what you'll plug in here will be the mean, right? So the mean is deterministic.
Okay, so
right?
it is deterministic. That's how I understood it. The language we're using is
Yeah, that's right, Uli, right? The mean is deterministic, and that's the mean we're going to use.
your confidence intervals and stuff, that's telling you like when you go to a different point parameter space, how does the likelihood change? That's that stuff. But I was asking like what is the likelihood for certain points? And I thought that was deterministic, but then we got a little confused, I guess, with the description. But I think it is, right? You get a particular value for the likelihood at a particular point parameter space. And you'll always get the same value no matter how many times you ask the emulator what the value is.
No, I mean, if you run the heavy iron model, which has a Monte Carlo freeze-out stage, if you run the model with exactly the same parameters and exactly the same conditions twice, you get different values for the ion spectrum.
Yes, but you only do it, you train the emulator once, and then the emulator is a thing that gives you a deterministic output for the model prediction. It has an uncertainty associated with it, but when you evaluate the likelihood, you get a number, right? Outer space.
Yes, I believe so.
And the uncertainty goes into this covariance also, but
I mean, you have to run the model sufficiently often so that you get a feeling for the variance of the output.
yeah, to train the emulator. But once you have it, the emulator output is
Yeah, right.
Yeah.
That's
Yes. Yeah, that's very important. Yes. So it's a probability distribution, but we assume it's Gaussian, right? So we can characterize it by the mean and the variance. So the mean will enter here, and the variance and the covariance will enter here. Yeah. That's right. So that was a bit of a detour. Is there any more questions about this, or is it clear?
So we should continue.
Okay, let's keep going.
Spend a lot of time.
Sounds good. All right, let me finish erasing. Let's see here. All right, so in practice, what you do for Bayesian inference, you choose a model, you choose a set of parameters, you choose priors for your parameters, and then you prepare the emulator. So the emulator is that blue band that we've been discussing. Choose a set of data, and then you compute your posterior here, and perhaps the evidence, which is the normalization of the posterior. And then you study it. Now, an example that I think many of you are familiar with, and if you're not, let me walk you through, is the viscosity, the shear and the ball viscosity. So if you think of heavy-ion collision as this multi-stage process, you have the collision of the nucleus, and at the end you have you measure a certain diffusion of hadrons, different species, different correlations, and so on. And we're trying to reconstruct what happens in the middle. We have a theoretical understanding of what happens. You have a certain early stage dynamics. It's still somewhat challenging to describe, but the work is being done on this to improve it. You have this hydrodynamic phase where your viscosities enter. So here we solve second order relativistic fluid dynamics, viscous hydrodynamics with shear and ball viscosity. And then you have a transition from hydrodynamics to hadrons to particles, and then there's additional dynamics in a transport. And if you're trying to constrain this shear and this ball viscosity, you still need to model the collision from beginning to end. And because of that, your constraint on your shear and ball viscosity will be indirectly affected by everything that happened, by any uncertainties you have in the initial condition, any uncertainties you have in any transition between the models. Now, there's been a number of studies, and I'm showing some results from the past 2 or 3 years. So this is the shear viscosity, this is the ball viscosity, they all as a function of temperature, and the different columns are different groups. On the left, you see those are results from Duke. In the middle, you have results from the trajectum group, and here you have results from Chatsky. And as you can see, I know not everybody here is a heavy end physicist, so maybe the exact value is not necessarily of prime interest to you, but you can certainly see that there are difference between the different constraints. Now, why is that? Well, as I said, of course, it depends on the choice of model, the choice of parameter, choice of data, and so on. So we can dissect up to a point what are the why the results are different. Now, Jiangyang, you asked earlier about modeling uncertainty, for example. So perhaps your initial conditions are imperfect, or perhaps you should use different types of initial condition. So I should highlight that all of these results here, the models by, in a way, historical standard are remarkably similar. They all use Trento initial condition, they all use very similar hydrodynamics, they all use hydrodynamic transport are quite similar, if not the same. And so in a way, the fact that even with pretty similar model, we get somewhat different result is sobering. It shows how sensitive we actually are to, in a way, modeling uncertainty. There are also differences in prior and more importantly, prioritization, and there's a difference in data selection. So let me walk through all of those one by one. Before I move on, I just want to put this in perspective. So of course, I'm focusing on things that we can improve. I don't want you to think that we have not learned a lot over the past couple of years, or we have not a lot of constraints. I think there's been an incredible amount of progress. And if you compare, for example, some of the plots I'm showing with some figures that were in the HotQC white paper, you can see we're discussing a pretty narrow band of possibilities. So there's been a lot of progress. So don't think that, don't take my remark as a general lack of progress. I'm focusing on things that we can improve. So the reason we have differences is in part a consequence of the pros and cons of Bayesian inference. So that's a slide I'll come back to very often. Let me actually come back to it a little later after I've discussed why we have those differences in these constraints here. So model differences that you asked Jiangyang, they're effectively a question of theoretical uncertainty. So the fact that people are making different choices for the initial conditions, or for the stage between the impact of nucleus and the initialization of hydro, the fact that no model is so clearly superior and dominant that everybody's using it is a reflection that we're still unsure exactly how to model this physics, that it's still a work in progress.
So the uncertainty on that we quote on the shear viscosity that's the uncertainty within the model space you're exploring, right? I mean,
that's exactly right.
You broaden the model space. Well, we cannot do this arbitrarily, but the question is, what are there parameters or aspect of the model that is still missing, right? I mean, in the initial condition, for example.
That's exactly right. And that's something I want to discuss even more later. But I think the benefits of Bayesian inference that it gives you very systematic and very reproducible results. I think a challenge is, in part, a communication challenge. I think we use, for example, to experimental communities spending maybe 10% of their time making a measurement and 90% of their time estimating the uncertainties. And that is not what, well, in a way, I think that the uncertainties that we fold into bands like this here don't necessarily have the same, they don't necessarily mean the same, in the sense that I think that if you ask an experimental, somebody in an experimental collaboration, if there's any significant uncertainty that they think they haven't included in their systematic uncertainty, I think in general there wouldn't be anything. Well, okay, I don't want to. Maybe I'm not in the know enough, but I think there's a lot of effort to systematically include everything that possibly can be included. If you ask somebody who does a Bayesian inference, can you think of any uncertainty that's not included? They can list 5.
I think one thing I was going to say, like, if the data, okay, if you do a data-driven approach, you see there's evidence from the data itself that the model is missing something. Then it's much more motivated. Okay, let's broaden this model space to include something that was missing. But my concern is that if we just arbitrarily include parameter in the model, that somehow, like, you know, whatever you put in, I want to see evidence from the data that supports this. It's not only through this complicated multi-parameter fit that you get, you know, some probability. But for example, the reason I'm saying like alpha bar, right? You really learn something that from the data directly, more transparently to see some impact of alpha bar on the initial condition. Then you say, okay, something missing, let me include it. But if I just put in a bunch of parameters, and okay, I can improve the description of the experimental data, but I still don't know, is this a little bit artificial?
I'd like to take a different perspective at it.
Mm-hmm.
I mean, I think just because you have a model that goes through the data points doesn't mean you don't have anything missing. And that really affects your conclusions when you extract some sort of posterior.
Yes.
So adding a bunch of parameters is not really productive if your goal is just to improve the fit to data. Like that doesn't really mean you're doing anything better. But if you add a bunch of parameters that are meaningful, that will make if you extract a posterior Bayesian inference, that will make it more robust. It can only make it more robust because you're just adding to the possibilities. And if you say, even if I add 30 more parameters, if 8 over S still has to be within this range, that's a powerful statement. Even if those parameters aren't obviously necessary just by looking at the fit of data.
No, the problem is that there's a lot of redundancy in the parameters. I mean, if you open up the parameter space, that they can trade off each other without any obvious support from the data, right? That's
and then you see that here.
You will see that in the Bayesian analysis.
Because that's the sort of thing you see.
Because if you look at the posterior probability distribution for the parameters and they turn out to be more or less flat,
right.
It tells you that you have introduced a parameter that is the data that you have in hand are not able to constrain.
Yeah, but whether you feed the data for the wrong reason, that's my concern. Because, for example, if we know V4, there's a nonlinear response coming from V2. But if you describe the V4 for wrong reason, you learn you're constraining basically some parameter of initial condition. But this is not the initial condition. It's the dynamics of the evolution, right? I just want to make sure like that there is always a clear explanation of why you're improving the data, and this is well motivated. It's not, putting some arbitrary parameter.
Yeah, it should be motivated, at least theoretically. I disagree that it has to be motivated by looking at the data, because that will mislead you.
Well,
Can mislead you.
yeah, but,
And I'd say also, I think people, when you mention the number of parameters that we sometimes have in our analysis, people are shocked. But for example, shear viscosity, it's a function. It's not, for longest time, we fitted it with a constant value, but it's a function of temperature. Now, maybe it doesn't vary so much that you need a lot of parameters to describe it. Maybe a flat, maybe a constant at over S is a reasonable approximation. But once you start trying to fit functions, and we know the shear viscosity, ball viscosity of QCD, we know from first principle, I mean, they have to be temperature dependent. There's a lot happening in this region of the phase diagram, which means even having 8 parameters to describe 2 functions of temperature is not that much freedom, actually.
But the way Bayesian analysis tells you that is that if you just take the RIC data at low energies and you calculate the most likely value for 8 over S, you get a different value than if you just take the LHC and you try to fit it with a constant value of 8 over S.
Yeah,
So
that's a good way.
From that Bayesian analysis that something must be going on with the eta S over S between these 2 energies. And then you ask yourself why. And the theorist in you tells you that you probe different temperature regions, so you start introducing a temperature dependence. But that is something that the data will not tell you that this is the way to do it. This is something that will have to, where you have to take experimental and theoretical prejudice and combine them into a reasonable way of improving the model.
Yeah.
Well, the data does tells you.
You know, it's temperature that controls that change.
Okay, I mean, you have to analyze it.
Wait, I think a very good example of this model dependent that you're asking about, Jiangyang, is actually not even considered often a parameter. So I think we're all many of you are familiar with the idea that when you transition from hydrodynamic to hydrodynamic transport, you have to reconstruct your hydrodynamic momentum distribution from your energy momentum tensor, and there's simply not enough information to do it without assumptions. So if you assume you're in equilibrium, you can do it because you know what your distributions are. But if you're out of equilibrium, you need some additional assumption to reconstruct your hydrodynamic momentum distribution.
Okay, fine, but you have a lot of freedom how you do that.
You have a lot of freedom how you do that. And for example, we tried to take that in, we didn't try, we took it into account. At least we tried different models, and we saw that, so we tried 3 different prescriptions to go from hydro to hydrodynamic transport. And we got those 3 different results for the shear and the ball viscosity. Now, that's a result, that's an uncertainty that's not included in any other Bayesian inference up to now. So already you were asking, is it model dependent? It's certainly model dependent. What other groups have, and of course what we have too. We don't have a perfect model either. So we're still at a stage where we're trying slowly to include all these different uncertainties to see if we can at least quantify. And the problem, of course, is that it doesn't mean that any of these prescription that we use is correct.
So this is only quantifying the uncertainty on the hydrogenization, right? Particularization.
But you have to understand it propagates, yes. So
So now that you look at this, you also see your prior space is not sufficient because a lot of this constraint, we're right sitting on the boundary of your prior space.
Well, insufficient. Well, I'd say it differently. If your posterior is really concentrated at the edge of your prior, certainly true, it's not big enough. I'd agree we could widen it, but there are some challenge to running
the bound
hydro.
viscosity, certainly the red and the blue on the upper limit is bounded, right, by your prior.
Yes, but that's exactly why it's so important to compare the prior and the posterior, which is something that we've really tried to to push, I think, in Jetscape and on other groups, because I think for example, in the past, you would only have one of these bands. Let's say you get the red, or more realistically, I think the green was what other groups would show. Would only get the green. You had no idea if the green was there because it was right at the edge of the prior, or because it was actual constraint from the data. Now here, because we plot the prior, it's obvious. We don't say that the red and the blue have to be below 0.15 here. We say we have no constraint, which are completely different statements. Yes, so that's very important. Yeah. All right. Any questions about this?
We have 25 minutes left.
Okay, that sounds good. Keep going. Priors, we discussed briefly priors earlier. Often we think of priors as maybe the range of parameters that you're exploring. People who are more familiar with Bayesian inference know it can be a distribution that you have on the probability distribution that you have on your parameter. Now you have to be careful because when you're parameterizing a function, for example, here, the way you parameterize your function will have an impact on what prior you end up with. And if you use a narrow prior or wide prior, it can make a big difference. But if you use different parameterization, it can make an even bigger difference. So let me show an example here, which is here the ball viscosity that we obtained here is actually quite broad at high temperature. But it's not quite as, we have some constraint at lower temperature. Now that's possible because we allowed an asymmetry in ball viscosity here. So we don't force, so often in the past, people would use a symmetric function for ball viscosity, which means that if you had constraint at low temperature, you had to have constraint at high temperature. Which means either you would have artificial constraint at high temperature, or you could have tension. And again, every analysis except ours is using symmetric ones, and it can bias your results. For shear, for shear viscosity, a different type of bias you can have, and this is actually more a communication problem. So in this analysis, we allowed shear viscosity at high temperature to have a negative slope, which is not what you expect from theoretical expectation. We have some calculation at PQCD, valid at very, very high temperature. The slope should increase. We have other reasons to think that the slope should increase. Now that means that we could have negative slope at high temperature here. Now it's totally correct and justifiable to disallow these negative slope, which means you would cut an entire range here of your prior, so of your posterior. So everything here you would cut purely based on your prior. Now you have to be careful mainly how you interpret the result. I think both results are useful. One result will tell you, I think the result where you cut this negative part might be the better one if you want to know what is the actual shear viscosity of QCD. Now, it's not the better one if you want to understand how much constraint you have on the viscosity of QCD from data. I think what this analysis showed, at least with the data we use, is that we didn't have a lot of constraint here. Which the narrower your prior is, the less you can tell if you have constraints. All right. So let me also show this result, which I think says a lot. So these are 90% credible intervals. It's the equivalent of just the outline of these bands I've been showing. And so the dashed line is the result you get if you use a symmetric ball viscosity, if you use a certain assumption for your parameterization of shear viscosity. And the solid line is what you get if you use these parameterization here that I'm showing on the left, which are more general. And you can see that it can have a very big effect, actually. Here, because you're forcing your bulk to be symmetric, the dashed line, again, if you have any constraint at low temperature, it forces you to have constraint at high temperature. In the other case, because we assume we can have asymmetry, it doesn't enforce those constraints. So those priors are important. Again, it's something that we just need to communicate better.
So from physics point of view, are there suggestions whether they should be symmetric or not symmetric? I mean, I don't know.
I don't think it should be symmetric.
Okay.
I don't think we have any reason to believe it should be symmetric.
Okay.
Yeah.
Very good.
Okay, so the last point I want to touch in this example is about data selection. So a lot of the difference that we could see in, if I go back in these three examples at the top. So the reason that even if we use pretty similar model, we ended up with somewhat different constraints. We certainly were using different data sets. Now, I think there's a general expectation that more data has to mean better results. And what I'm going to say might be a little controversial, but hear me out. So I think we have to be careful about this in the sense that it's only true if your model is perfect and if your model is as good to describe everything else. So let me give an example. If I take my multi-stage model of heavy-ion collision and I decide that I'm fitting minimum bias proton-proton collision with it, I include that in my Bayesian inference, I will get probably very good constraints. I'll get right in that corner here because there'll be most likely a lot of tension in the model trying to compensate for the fact that the model is probably not made to describe minimum bias proton-proton collision. Now, it's an extreme example. So of course, I don't think anybody object to the fact that you shouldn't include data that are obviously not described, that shouldn't be described by your model. The point I want to make is that without these theories, there's a continuum between this. I think our model likely work better for ultracentral collision than for peripheral collision. I think our model probably works better for large system than small system. I think we should compare with all these systems. But if the aim is to obtain the best possible constraint on the parameter, I don't know if we should be necessarily including data that we think are pushing our model at the edge.
I agree with this because because the model is not perfect. That means the missing ingredients in the model may be amplified for particular data, right? But for other data, let's say the V2 or the bulk one, it may not be. Maybe actually it's an improvement, but then for some other observer, it may actually make it worse. If you are interested in like the high order correlations, okay, like high order many multi-particle correlation, which are influenced by the nonlinear response, but also the shear bulk viscosity. There, you could have a disagreement because there are some missing ingredients. But if you assign equal weight in your calculation chi-square, then your bias actually, the observer you're supposed to describe well, right? Because you will get a wrong answer because one should know what observables should be described by the model first. Yeah, make a choice.
Yeah, and I think, okay, I don't know if I thought this would be a more controversial point. It turned out to be. I'm glad it's not. Of course, I think it makes people uncomfortable because I don't think we should be picking and choosing data carelessly. That's a recipe for, in a way, tunnel vision and getting what you want out of the data. But you have to be very careful. And I think certainly what we've experienced doing Bayesian inference is that people will just tell you, group X compared with that data set, they have a broader data set, their result has to be better. I don't know. I think we should always compare with the broader set of measurement that we can, but we should also be careful with our model's applicability, and think carefully about it. And yeah. Okay, so those are reasons why we, even with relatively similar models, we're getting different constraints. Now, I think part of our problem, again, is with communicating the results. It's something that I think we can do better, but there's a lot of opportunities for this. I think a classic example is, for example, the initial time here. So you remember that there's a transition time between at which you initialize hydrodynamics, and we'll often call this tau zero, or the initial time of hydrodynamics. Now, this parameter has a number of different values, and if you ask most theorists, it's a pretty ill-defined parameter, actually. The problem is that I think intrinsically, if you publish results with a nice error band, people tend to attribute to it more meaning than there should be. So you can hear people say, well, this group has showed that the initial time of hydro is 1 Fermi. And obviously it's something that if people think this, is because we haven't explained well. So it's something you always have to be careful about. Now, I'm mentioning this because I think there's been a lot of ink and discussion about some of the results that some group, that Jetscape, for example, obtained about initial conditions, which is, I think, of interest for everybody here. For example, I think we got grief for this d-min is effectively the minimum distance that you try to have between your nucleons as you sample them from your nucleus. And the result that you see is a marginalized posterior. So if you integrate over all the other parameters and you just plot the probability for this parameter, you can see it's relatively flat. And the different color bands are for, if I go back here, they're for different prescription that we use here for the transition between hydro and hadrons. So just a reminder that all of this propagates. So of course, our initial conditions are dependent on this too. The constraint we extract on the initial condition are dependent on what happens at the end of the collision. And there's certainly a maximum value here, but the distribution is relatively flat. So I think there were criticism that we're extracting values that were nonsensical. And I think it's more about communicating that we don't really have any constraint on this parameter. And it's not, people shouldn't read, obviously we don't think that you should have 2 Fermi between your each one of your nucleon. That would be problematic. I think there's also software questions in here. So let me not discuss this too much, because your model should be able to distinguish whether you force your nucleon to be 2 Fermi or 1 Fermi apart or 0.1 Fermi apart. So I think it's also a question of how the model actually places the nucleons. I think the width has been much more controversial. So I think there's been publications on this too. And the question is, so we obtain well-defined constraints on this width, and this width is roughly the, well, unfortunately, this width plays a dual role in the Trento model that everybody uses in Bayesian inference for describing the impact of nucleus. And this dual role is, it determines over what radius you deposit the energy from your nucleon impact, but also it's also used as to determine whether you have a binary collision, whether you have an interaction. Now, neither of these quantities are the proton radius, of course, or nucleon radius. They're related, but they're not these quantities. And because of the interpretation of initial condition, because we use, because effectively all of this is used to initialize the hydrodynamics through, in a way, there's, one should be very careful interpreting the result. So I think it's, again, I think it's a failure of communication if people are telling us that it doesn't make any sense that we're getting a proton radius that is larger a certain value. I think we have to make clear that what we extract, we're not trying to extract the radius of the proton, of course, and that
But what is the reason you prefer such big W in your approach? What is the fundamental reason?
no, clearly, I mean, that's been a, let's see, I think okay, I'll have to look again at, we did a sensitivity analysis and I forget the result. I think it's even the VNs that have some preference.
So maybe there are particular observer that prefer this. I just don't know.
Yeah.
It's
So
a BT or
PT fluctuations?
BT fluctuation?
I'm sorry.
PT fluctuations? Is this the stability?
Could be. Maybe I'll ask Matt if he can take a look at the paper and come back to us. We have the answer. I forgot to put the plot in the slides. But yeah, so we certainly have constraints. I think the problem is not that we don't have constraints, it's that we don't necessarily, I think we don't necessarily understand perhaps, well, we shouldn't assign a direct meaning to a parameter, but also I think we have to be honest that there's still a lot of uncertainty in initial conditions of heavy end collision. So we're using a combination of Trento and free streaming. We shouldn't initially think that this is the ultimate description that can unambiguously match the nucleon radius to the initial stage of hydrodynamics. Matt, could you find the sensitivity?
Yeah, I think so.
Okay, we can
You want me to
continue.
share,
and,
Well, maybe we can discuss it. Yeah. Okay. All right. So opportunities and outlook. So I think Bayesian inference have a lot for them. They really, one of the big step forward is systematic and reproducible constraints on the model parameters. So if you're given a set of data and you're given the model, and nowadays there's really an effort to make sure models are public, that that everything is public so that people can reproduce, you can get reproducible constraints on the model parameter, which is difficult, if not impossible, when you do a chi-bi. We can do a very good job in terms of propagating uncertainties as well. It scales very well with when you have larger number of measurements and larger number of model parameters. There's also opportunities here that I'll discuss in the coming slide. Let me mention a couple of challenges, which are certainly it's numerically expensive, and we have it comes at a price that we use emulation, that our models are expensive and we have to replace a model by Gaussian processes. We do introduce additional uncertainty in the problem. And that can be a complicating factor when we try to interpret the uncertainties that we're obtaining. So the uncertainties that we see on the parameters, they include this emulation uncertainty, which is not always negligible.
Yeah, but I wouldn't call it introducing additional uncertainty. If the model is expensive, then the model evaluation is necessarily placed at points, parameter values that are far apart, which makes it more uncertain to predict what the model would predict in between.
So you mean there's no way around?
There's nothing you can do about it.
Yeah, I would agree with that. Yes. I think one of the challenges as well in terms of communicating the meaning of uncertainties, which again comes back to your question, Zhang, about how much it depends on the model, on the choice of model. And also communicating the meaning of a parameter, which is what I've just been discussing. Now, let me mention experimental design, because I think it's something we haven't done a lot, and I think it's very interesting. I think one of the pioneering work in heavy end physics has been this work by Scott Pratt, where he looked at effectively if you, let me move this here. So if you change a parameter, how much the observable changes, and that already gives you some sense of which parameters, which observables are the most sensitive to which parameter. So here you have a list of different measurement, pi and multi-t, some mean PT, and so on. And here you had the equation of state parameter, viscosity parameter, and some initial condition parameters. So that was a good step, but they went further and they tried to, of course, the result that you get also depend on how sensitive your model is to the parameter, how big your uncertainties already is. So if your uncertainty is already pretty small, there's no gain reducing it. So they made additional plots like this, which were a way to quantify, basically, if you change larger absolute value to measurement. Right, so effectively, if you change if you reduce the uncertainty on the measurement, how much do you improve your constraints on the parameter? I think it's something that's used quite a bit in other fields. It's something that I think we're just starting to use. I think I'd point to this nice paper by the Trajectum group, where they try to use simulated oxygen and nitrogen data. So what you do is you have, let's say you compare with heavy-ion collision, you compare with lead-lead data, and you do a Bayesian inference, and then you use your model to generate some oxygen-oxygen calculation and use that as data, and you do a calibration on this as well and the lead-lead. So effectively what you can find is how much better are your constraints on your initial conditions or your viscosity if you include your oxygen data. So I think it's something, again, we haven't explored very much, but I think there's a lot to do there. Model mixing, perhaps you'll hear more about it. Uli's in the audience, and I think it's a very interesting idea. So think of it, and it's a partial answer to handling model uncertainties. So what if your model is better at predicting certain observable than others? So what if your model simply works better in certain regions of parameter space? If you compare that model with data and some other model with data, you compare the best and the worst part of both model and with data. What you can do is to try perhaps to compare the best part of one model with data in some parameter range and use model B in some other parameter range, and that can in a way create a hybrid, that can create a model that would be difficult to make purely from a theoretical perspective, but that can give you a sense and give you a way to combine the best of the two models and see if what you can learn about your model from this.
Does this approach actually means the number of parameters effectively is a sum of the number of parameters in the two models, or is simpler than that?
No, I don't think so. Think of it as, this is a simple example, but think of it as, let's say you have viscosity here at over S, some quantification of it over S, use model A here and model B here. So when you're at large viscosity, use a certain model. So in a way, you don't have more parameters. It's just that in different range of the parameter space, you will use a different model. And you will let the model try to decide in what, well, you can let the model try to decide in what range it should use one and what range it should use the other one. So you can learn a lot from this.
For these ones, because the definition of parameter are common. But suppose the upperclassman versus Trento. I know one can approximate the upperclassman in some sense by this TA, TB product with some power, but they probably have a different set of parameters, right?
That's right, but you can get away from the parameters by making the posterior directly for the observables. And that means different models would average over probability distributions for different parameters and give you a predicted outcome for the observers, and then you mix these in different regions of the parameter, of the physical parameter space, not the market parameter space.
to explore the correlation between the models. Right? Because there's some aspect which are orthogonal, there's some aspect.
How you interpret what is coming out is a big question of discussion. So this is, I don't want to comment on this at this point.
Okay, suppose your model mixing prefer 50-50 mixing of two models. How do we then interpret this result?
Right. I think at that point, you have to start thinking more about your model and how to. So I don't think it's the final solution in the sense that I don't think you'll ever come out and say my model is 50% IP Plasma, 50% Trento. But it can give you a sense of what feature of which model you need to use, especially if, let's say, IP Plasma does great on a certain set of observable and does much better on a different set of, and Trento does better on a different set. You can try to see which features of a model are most important for the observable, which features of the other model. So I think it's a tool to learn about your model. Uli can add to this if he feels it's incomplete, but I think it's a tool.
It's a perfect subject for discussion in the afternoon.
Yeah,
we can talk a lot about things we don't understand.
Sounds good.
Yeah.
So let me go through the last slide and then my brief summary slide. So there's been a lot of work trying to reduce the cost of numerical of Bayesian inference, which makes it a barrier. The cost really makes it a barrier for certain groups. You have to have access to either a large amount of CPU time, or you have to be able to share calculations. There's been a number of interesting studies in terms of transfer learning, multi-fidelity emulation, adaptive sampling. Recently, we had a paper at Duke with a summer student trying to optimize the statistical and interpolation uncertainty. This is more on the technical side, so if you have any question, we can discuss it. I didn't prepare initially more slides about this. Just want to say it is important. If something can be done on a laptop or something takes days on a supercomputer, it makes a difference in who can use it. So I think the efforts of all these groups will benefit everyone in the future. So let me stop here with this summary, which I think are the benefits and the challenges of Bayesian inference. I think it can do. I think they are a very important tool, especially in terms of quantifying the uncertainties. There's many things we haven't explored very much yet in terms of model mixing. I didn't talk about model selection, but I think it comes back to this idea of trying to use the data to see if certain models are preferred. Experimental design, which I discussed briefly. We have to address, I think, the challenges too. We have to take that into account, certainly the numerical cost, but also I think a lot of the effort is in communicating the result to make sure there's no misunderstanding in terms of what's included in the uncertainty bands. All right, let me stop here. I'm happy to keep discussing for the next 15 minutes and then later.
So our question, so experimental design, what does this term mean? Are you mean you're picking and choose observables from experimental data, or you mean some doing new future experiment?
So, right, so it's about guiding. So, for example, if before a measurement is made, before a new measurement is made, we can presumably compute it. And we can already tell you, if we compute it, we can give you a sense of how much this observable can help constrain parameter X, Y, Z. Now, there's an assumption in here, which is we assume that our model is still describing this physics properly. But in general, I think it's better to have guidance from an imperfect model than no guidance.
This is the guidance for improving the model, or
Yeah,
this is
yes.
okay.
Well, I mean, let me try to phrase this a little bit differently than what JF just said. So experiments are expensive, and so you do a model analysis of existing data, and there are certain parameters that are well constrained by the experiments, and there are certain parameters that are not constrained. So how do I get better constraints on these parameters? For that, you would have to identify particular measurements that would do that. Now, the usual way we do that is we calculate the various observers for different possible experiments, and then we look at the output, usually just for 1 or 2 observers, which we somehow expect to be most sensitive, and give some rough guidance that this should be referred. But that doesn't take into account all the correlations between observers, different observers and different parameters. And what the Bayesian analysis allows you to do is to give you a quantitative assessment of how much information you will gain on all particular parameters once you postulate experiments at certain parameter values. For example, add a point with oxygen compared to not having oxygen.
So there are probably 2 aspects. One is what you said. The other will be what other measurement you can do in the existing data, for example.
Yes, you could come up with completely new observers.
Yeah.
Theorists can do that all the time, and experimentalists will probably need to build a particular gadgets to measure that. And before they do that, they want to know that it will really pay off. And
Yes.
So it's also non-trivial that a new observable will actually contain new information, even if it looks very different. Like, for example, this event plane angles observable. So this is cosine to phi 2 minus some other angle. Like, in principle, you could come up with some kind of flow distribution where these angles are basically random. But it turns out that if you do a Bayesian analysis and you fit to, for example, V2, V3, V4, and MPTs, etc., then your prediction for these angles is pretty good. So actually, it looks like if you were to include them in Bayesian analysis, you would probably not gain much because they're already quite well described. So apparently, somehow the information contained in them is sort of the same information that you already had, which I, to this point, don't really understand why that would be the case for that particular observable. But, without a Bayesian analysis, that's very hard to understand why that would be the case.
Right.
Yeah, Govert, did you try new observable for oxygen, or did you use the typical, let's say, multiply steam PT?
Yeah, we just used I think it was particle yields for pion, kaon, proton, and MPT for pion, kaon, proton, and then integrated V2 and V3, I think. It's been more than a year, so.
Yeah. So Django, for example, if somebody thinks that there's a perfect observable in oxygen that would really make a difference, you could just ask Govert, compute it, try to do a Bayesian inference, and I'll tell you at least, yeah.
Also, one thing is we have to guess, like, we are not experimentalists, so we don't know what experimental error we should use in the Bayesian analysis principle. We just guessed some reasonable number.
But that's, in a way, that's also a strength, which is you can tell people you need to measure this to 2% if you want any contribution to constraining the parameters, or 20% is enough. So you can do pretty evolved tests with this, actually, and give a lot of information to the experimental community. Yeah, it's very nice that we're finally seeing some of these.
Very good. Yeah, go ahead.
Yeah, I have another comment on something else. So you mentioned about the data selection.
Yeah.
There, I think what is also important is to, like, for example, what we do is we usually do multiple Bayesian analyses, which with slightly different assumptions. So, for example, I'll be talking about this tomorrow about these weights we introduced that we knew that would be controversial. So what you do is you do the Bayesian analysis with the weights, you do it without the weights, and you show both results and see if it's sort of the same. And if it doesn't depend much, then you have more confidence that it's probably correct. But then, for example, we also always fix parameters at certain values. So, for example, we see like what happens if you say the shear viscosity has to be the absolute lowest value that's in the prior. What happens to the other parameters? Do they change? And then, yeah, by by having like an ensemble of Bayesian analyses, you can sort of also get more confidence that the conclusions you draw are actually robust against, for example, if you do something unreasonable, like saying shear viscosity is 0.
Yeah, and I think that's very important. I think we're often interested in the final result, but there's so much information we have. You can, as you said, drop observables, change the weighting. You can, and you should really, we should really share those results. People can learn a lot about this.
I mean, I think what Gobert just said is very important because
Yeah.
it illustrates a point that you also made, but maybe not quite as explicitly as I would do it, that all Bayesian analysis results depend on what you put in for the prior. So they're conditional on the prior. And so when you, for example, put in a prior prejudice that the shear viscosity should be at the lower theoretically allowed end or so, you are doing the analysis with a different prior than the other one, and that gives you sensitivity. That gives you a feeling for the sensitivity to the prior, which is not what you want. You want to, when you talk about a robust result, you think about one that is not sensitive to your prior assumptions. But if you find out that it's very sensitive to the prior assumptions, then it's a big warning flag. And this is something. This is a change of perception that has to go through the entire community, that what you draw as a conclusion is always depending on what you put in as prior assumptions. And these are usually not stated. And what Bayesian analysis allows you to do is to state them and to include them in a statistically consistent way with all the other stochastic uncertainties that you have to deal with.